Hi, my name is Diane Enzastiga. I am an undergraduate senior at Colorado State University. My research focuses on how increased gait variability contributes to deficits in bilateral gait coordination after stroke. I have conducted this work under the mentorship of Dr. Lodha and Dr. Patel at the Movement Neuroscience Rehabilitation Lab. Over the course of my research with stroke, one thing that really stuck out to me is that stroke can impact anybody. The story of Adam Fontaine really jumped out at me. Adam had a stroke when he was very young. His stroke caused impairments in the lower extremity motor function and also contributed to deficits in walking and loss of functional independence. Coordination of the lower extremity is something many people take for granted. It is necessary in order to perform everyday activities like walking. Coordination between the lower limbs, otherwise known as bilateral gait coordination, measures the degree to which the two legs are moving in a synchronous manner. After stroke, bilateral gait coordination is often impaired, which can unfortunately lead to an increased risk of falls and reduced functional mobility in people with stroke. Human gait in general is characterized by small stride to stride fluctuations. Not every step or stride is going to be the exact same. These fluctuations are known as gait variability. People with stroke exhibit increased variability in their gait, both spatially and temporally, which is indicative of a more unstable walking pattern and could likely impair bilateral gait coordination after stroke. We had two main questions we wanted to answer with our research. One, does stroke impact both spatial and temporal gait variability? And two, whether spatial or temporal variability contributes to reduced bilateral gait coordination in stroke. We hypothesized that there would be increased spatial gait variability in people with stroke compared to healthy controls. We also hypothesized that increased spatial gait variability would be correlated with deficits in bilateral gait coordination seen after stroke. In our study, we had 22 people in their chronic phase of stroke who could ambulate independently and 22 healthy age-matched controls. The FMA for lower extremity measures the degree of lower extremity motor impairment. The average score of 27 indicates that the stroke group had mild to moderate impairment of the lower extremity. FAI, or French Activities Index, indicates the level of participation in daily activities of living, and the stroke group showed high levels of participation. All participants performed an overground walking task in which they walked 7 meters at their natural walking pace. We utilized wearable sensors to measure gait variables such as stride length and stride time in order to calculate each participant's phase values. The ideal phase is 180 degrees, which indicates that the participant's step time is exactly half of their stride time. Phase data was then used to compute the phase coordination index for each participant. The two main outcomes we examined were gait variability and bilateral gait coordination. Gait variability was measured as stride length coefficient of variation and stride time coefficient of variation. Bilateral gait coordination was quantified by the phase coordination index, which measures the degree to which both of the lower limbs are moving synchronously. The phase coordination index, otherwise known as PCI, can be calculated by summating the coefficient of variation of phase and the deviation from the ideal phase of 180 degrees. Larger deviation from 180 degrees indicates less coordinated movements. The higher the CV of phase, and the larger the deviation from the ideal phase of 180 degrees, the higher the PCI value, which signifies poorer coordination of the lower limbs. Here is a data sample taken from a control and a stroke individual from our study. Just to give a visual representation of phase, this is what it looks like compared between the stroke individual and the control participant. Each point represents phase that was calculated for a gait cycle. As you can see, the individual with stroke shows a much larger deviation from 180 degrees, as well as a much more variable phase compared to the control. From here on, for the rest of the results, I will be using dark green color to indicate control and light green for stroke data. Here are the results comparing stride length variability between the controls and the stroke group. The stroke group on the right showed a significantly greater stride length variability compared to the control group. This indicates that stroke survivors have increased spatial gait variability compared to controls. Here, we have the results of stride time variability, a temporal gait measure. There was no significant difference found between the stroke and the control groups. This tells us that stroke individuals only show greater gait variability spatially as opposed to temporally. For bilateral gait coordination measure with the phase coordination index, we found that people with stroke show a significantly higher PCI value compared to controls. This signifies that stroke survivors have reduced coordination of the lower extremity compared to healthy individuals. The first question we aimed to answer with our study was, does stroke impact spatial and temporal gait variability? Our results revealed that stroke predominantly impacts spatial rather than temporal gait variability. For the second question, we determined the association between gait variability and bilateral gait coordination. Here, we found that stride length variability was related to bilateral gait coordination. We found a significant association between stride length coefficient of variation and the phase coordination index. These results demonstrate that spatial gait variability is correlated to reduced bilateral gait coordination in people with stroke. Another regression was conducted among the stroke group for stride time CV and PCI. However, no relationship was found indicating that temporal variability has no association with reduced bilateral gait coordination seen in stroke. For our second question, whether spatial or temporal variability contributes to bilateral gait coordination in stroke, we found that spatial, but not temporal variability, is associated with reduced bilateral gait coordination. While previous studies have determined that increased gait variability is seen in stroke, as well as reduced inner limb coordination, it had yet to be determined the type of variability and how this is associated with reduced coordination. Our study reveals that bilateral gait coordination and spatial gait variability are impaired in stroke. The reduced consistency of the spatial gait pattern contributes to the timing deficits among the lower extremity after stroke. The novel work we have conducted has many important implications for those living with stroke. Understanding the specific gait dysfunctions seen in stroke can lead to the development of targeted interventions that will help to promote safer mobility after stroke. So, coming back to Adam, several years later, Adam competed in the Paralympics after recovering from his stroke. Understanding how increased gait variability contributes to reduced gait coordination will enable us to help many others regain walking mobility after stroke. I hope you all learned something new and interesting today. Thank you, everyone, for listening to my presentation. I would be happy to answer any questions.